Uranus is one of the strangest planets in the entire solar system. It spins on its side. Its magnetic field is completely misaligned. Its internal heat was missing for decades. And despite nearly 40 years of research since the only spacecraft to ever visit it, astronomers still do not fully understand why it behaves this way. It is the ice giant that broke every rule in the solar system. And we still do not know why. It does not spin the way the others spin. It does not glow the way the others glow. It does not hold its magnetic field the way any self-respecting planet should. And for the longest time, nobody even bothered to look at it, because from a distance, it looked like nothing. A pale blue dot hanging in the outer dark, featureless and still, like a marble someone forgot at the edge of a table. And if you think you already know everything there is to know about it, let me ask you something. Why does it roll on its side? Not a gentle lean like Earth, not a modest tilt like Mars. Uranus is tipped almost completely over, spinning at roughly 98 degrees from where it should be. Imagine a top that fell on its side but somehow kept going. That is Uranus, every single day, for 4.5 billion years. But here is the thing nobody tells you. The tilt is only the beginning. The deeper you look at this planet, the stranger it gets. Its magnetic field does not line up with its center. Its internal heat is almost entirely missing. Its moons should not exist in the orbits they occupy. Its rings are so dark that they are nearly invisible. And the one time we ever got close enough to study it, we caught it during what scientists now believe was a once-in-a-lifetime cosmic event that may have distorted everything we thought we learned. Uranus is not just the forgotten planet. It is the broken one, and no one can agree on what broke it. So tonight, let us drift out to the cold edge of our solar system, past Jupiter, past Saturn, past the last echoes of sunlight that feel like anything at all. Let us visit the planet that science cannot quite explain, the ice giant that rewrote the rules and then hid the evidence in 4 billion years of silence. Because out there, in the dark, something happened. Something enormous, something violent, and whatever it was, it left behind a world unlike anything else we have ever seen. Let us begin. Every planet tells a story. Jupiter tells a story of overwhelming power, a world so massive it could swallow every other planet combined and still have room to spare. Saturn tells a story of elegance, its rings stretching outward like the pages of a book written in ice and dust. Mars tells a story of loss, a world that once had rivers and skies, and maybe, just maybe, something alive, before it all dried up and blew away. But Uranus tells a different kind of story. It tells the story of something that went wrong. Tired of waking up at 3 a.m. because your sleep video ended? Cosmic Drifts Beyond the Stars plays for hours. No ads, no interruptions, no reaching for your phone. 5 full night sleep experiences, one-time purchase. Begin now at mycosmicdrift.com. To understand why, you first have to understand how planets are supposed to work. In the early solar system, roughly 4.5 billion years ago, everything was chaos. A massive cloud of gas and dust collapsed under its own gravity, and at its center, our sun ignited. Around it, the leftover material began to swirl. Grains of dust stuck together. Pebbles became boulders. Boulders became planetesimals, and planetesimals, over millions of years of collisions and gravitational tugging, became the worlds we know today. This process, called accretion, follows a pattern. The planets that formed closest to the sun ended up small and rocky because the intense heat burned away the lighter gases. Mercury, Venus, Earth, Mars, small, dense and solid. Farther out, beyond a boundary scientists call the frost line, things were different. It was cold enough for ice to form, for gases to stick around, for worlds to grow massive. Jupiter and Saturn ballooned into gas giants, pulling in enormous atmospheres of hydrogen and helium. And even farther out, in the cold, quiet reaches of the solar system, 2 more worlds took shape, not as large as Jupiter, not as flashy as Saturn, but substantial, dense, strange. These were the ice giants, Uranus and Neptune, built not from hydrogen and helium alone, but from heavier stuff, water, methane and ammonia, compressed under unimaginable pressure into something that is not quite ice and not quite liquid, and not quite anything we have a good word for. Now, here is where it gets interesting. In this model, every planet should spin more or less upright. The cloud of material that formed each world was rotating in roughly the same direction, like a giant cosmic record player. That spin gets passed down to the planets. Earth tilts about 23 degrees. Mars tilts about 25. Even Saturn, with all its flamboyance, only tilts about 27 degrees. These are modest angles, gentle leans, like a person resting their head against a window on a long train ride. Uranus tilts 98 degrees. That is not a lean. That is a collapse. That is a planet lying on its back, spinning like a wheel rolling along the ground, instead of a top standing tall. And nothing in the standard model of planet formation can explain it. You do not get a 98-degree tilt from the slow, steady accumulation of dust and gas. You do not get it from gravitational tugging. You do not get it from anything ordinary. You get it from violence. But we will come back to that. Because first, there is something else about Uranus that does not make sense. Something that puzzled scientists for decades and only recently began to reveal its secrets. And it has to do with heat, or rather, the almost complete absence of it. Every giant planet in our solar system radiates heat. This is expected. When planets form, they are born hot. The process of accretion converts gravitational energy into thermal energy. Basically, when stuff falls together, it heats up. And for a planet the size of Uranus, that heat should linger for billions of years, slowly leaking out into space like warmth, escaping from a house on a winter night. Jupiter radiates roughly twice as much energy as it receives from the Sun. Saturn radiates about 1.8 times as much. Neptune, even farther from the Sun and colder on the outside, radiates roughly 2.6 times as much energy as it absorbs. These planets are still cooling down from their births. Their interiors are furnaces, and the heat is slowly working its way out. But when Voyager 2 flew past Uranus in January of 1986, it measured something strange. Uranus appeared to radiate almost exactly as much energy as it received from the Sun. No excess, no leftover glow, no internal furnace. It was as if someone had reached inside the planet and switched off the engine. For decades, this was one of the great puzzles of planetary science. How could a planet the size of Uranus have no internal heat? Every model of giant planet formation said it should. Every comparison to its neighbors said it should. And yet, the data from Voyager seemed clear. Uranus was cold, not just on the outside, where temperatures in the upper atmosphere drop to around negative 224 degrees Celsius, making it one of the coldest places in the solar system. But cold on the inside too, or at least, that is what it looked like. Scientists proposed several explanations. Maybe Uranus was much older than the other planets and had simply cooled off completely. Maybe its internal structure was different, with layers that prevented heat from rising to the surface. a kind of thermal blanket locked deep inside. Or maybe, just maybe, the same catastrophic event that knocked it on its side had also ripped the heat right out of it, turning the planet inside out in a way that let all that primordial warmth escape in a single, violent moment billions of years ago. For a long time, none of these ideas could be confirmed, because Voyager 2 was the only spacecraft ever to visit Uranus. One flyby, a few hours of close observations, a handful of photographs and measurements, and then silence. Nearly 40 years of silence. But science does not stand still, even when spacecraft do. And recently, 2 independent teams of researchers went back to the data, armed with decades of additional observations from ground-based telescopes, the Hubble Space Telescope, and advanced computer models that did not exist in 1986. What they found changed the story. Uranus does have internal heat. It is not much, not compared to Jupiter or Saturn or even Neptune. The planet appears to emit about 12.5% more energy than it absorbs from the Sun. That might not sound like a lot, and compared to Neptune, which emits more than 160% excess, it is modest, but it is there. Uranus is not thermally dead. It is just quiet, whisper quiet, as if the furnace inside is still burning, but the damper has been almost completely closed. The reason Voyager missed it comes down to 2 things. First, the instruments on Voyager 2 measured the planet's thermal emission over a narrow range of wavelengths, and they only had one chance to do it. Everything we thought we knew about Uranus's heat budget was based on a single data point from a single flyby. Second, and this is the part that makes you stop and think, Uranus has seasons, not like Earth's seasons, with their gentle shifts in temperature and daylight. Uranus has the most extreme seasons in the entire solar system. Because of its massive tilt, each pole of Uranus faces the Sun for roughly 21 years at a time, while the other pole is plunged into total darkness. Imagine a planet where one half bakes in continuous sunlight for 2 decades, while the other half sits in absolute night. Then, slowly, the planet rolls over, and the process reverses. This means that the amount of sunlight Uranus absorbs changes dramatically over the course of its 84-year orbit. And because the heat budget depends on comparing what comes in from the Sun with what goes out from inside, getting that calculation wrong by even a small amount can make internal heat seem to vanish. The researchers found that Uranus is actually more reflective than anyone had estimated. It bounces more sunlight back into space than Voyager suggested, which means it absorbs less solar energy, which means the planet needs less internal heat to explain its temperature. And when you crunch the numbers with better data, that missing heat suddenly reappears. Not a lot of it, but enough. Enough to confirm that Uranus is still cooling down from its birth, like every other giant planet. But whatever happened to it, whatever knocked it over and scrambled its insides, also robbed it of most of its warmth. The fire is still there, but it is a candle where there should be a bonfire. And that raises a question. What could do that to a planet? Now, let us pause here for a moment. Let us take a breath, because we are about to step into one of the most dramatic chapters in the history of our solar system. A chapter written not in gentle accumulation, but in catastrophic violence. And to understand it, we need to go back, way back. Back to a time when the solar system was young and wild, and the planets had not yet settled into the calm, predictable orbits we see today. The early solar system was a shooting gallery. Planets did not simply form and stay put. They migrated. They drifted inward and outward, pushed and pulled by gravitational interactions with each other and with the vast disk of gas and debris that surrounded the young sun. Jupiter may have wandered inward before being tugged back out by Saturn. Neptune may have swapped places with Uranus at some point, ending up farther from the Sun than where it originally formed. The entire outer solar system was in flux, a cosmic game of musical chairs played with worlds the size of small stars, and in this chaos, collisions were inevitable. We know this because we see the evidence everywhere. The Moon was almost certainly formed when a Mars-sized body slammed into the early Earth. Mercury's enormous iron core may be the result of a giant impact that stripped away most of its rocky mantle. Even Mars shows signs of a massive ancient impact in his northern hemisphere, a basin so vast it covers nearly 40% of the planet's surface. So when scientists looked at Uranus and saw a planet tipped on its side with almost no internal heat and a magnetic field that made no sense, the leading theory was not complicated. Something hit it, something enormous. The giant impact hypothesis for Uranus suggests that roughly 4 billion years ago, a protoplanet at least twice the mass of Earth collided with Uranus. Not a glancing blow, not a gentle merger. A full-on world-reshaping impact that delivered so much energy and angular momentum that it knocked the planet completely sideways. Think about what that means for a moment. A body twice the size of Earth, slamming into a planet 4 times the diameter of Earth at speeds that may have exceeded tens of kilometers per second. The energy released in such a collision would have been beyond anything we can meaningfully comprehend. It would have been enough to melt the outer layers of Uranus, to blow a significant fraction of its atmosphere into space, to fundamentally reorganize the planet's interior. And it would have been enough to tip it over. Computer simulations of this event paint a vivid picture. In the moments after impact, the collision would have created an enormous disk of debris around Uranus, a ring of shattered rock and ice and vaporized gas, spiraling around a planet that was now spinning in a direction it had never spun before. The shock waves would have rippled through the interior, disrupting whatever layered structure had built up over hundreds of millions of years of quiet formation. But here is the part that connects back to the heat mystery. Some simulations suggest that the impact was so violent that it mixed the interior of Uranus in a way that accelerated its cooling. Normally, a giant planet cools slowly because its internal structure acts like insulation, with dense, hot material at the center and lighter, cooler material on the outside. Heat has to work its way through all those layers, and that takes billions of years. But if a giant impact stirred the interior like a cosmic spoon, bringing hot material to the surface and cold material down deep, the planet could have lost a huge amount of heat very quickly in the aftermath of the collision. It would have glowed briefly, with an intensity far beyond what a planet of its size should produce. And then, over the next few 100 million years, it would have cooled down to a state where its internal heat was far lower than it should be, far lower than Neptune, far lower than Saturn, far lower than any giant planet that had simply formed and sat still. The impact did not just tip Uranus over. It may have bled it dry. But wait, there is another piece of this puzzle. Because if you look at Uranus from the inside out, the strangeness does not stop at the heat. It gets weirder. Let us talk about the magnetic field. Every planet in our solar system with a significant magnetic field generates it the same way. Deep in the planet's interior, there is a region of electrically conducting fluid. For Earth, it is molten iron in the outer core. For Jupiter and Saturn, it is metallic hydrogen, compressed under such incredible pressure that hydrogen atoms lose their electrons and behave like a liquid metal. This conducting fluid churns and flows driven by convection and the planet's rotation, and that motion generates a magnetic field through a process called the dynamo effect. In every case, the magnetic field is roughly aligned with the planet's axis of rotation. Earth's magnetic poles are close to its geographic poles. Jupiter's are a bit offset, but still recognizable. Saturn's magnetic field is almost perfectly aligned with its spin axis, so symmetrical it puzzled scientists for years. And then there is Uranus. The magnetic field of Uranus is not aligned with its rotation axis. It is tilted about 59 degrees away from it, and more than that, it does not even pass through the center of the planet. The magnetic axis is offset from the planet's center by roughly a third of the planet's radius. Imagine a bar magnet shoved off to one side inside a ball and tilted at a steep angle. That is what the magnetic field of Uranus looks like. This is deeply strange, and for a long time, scientists assumed it was somehow related to the extreme tilt of the planet itself. Maybe the impact that tipped Uranus over also disrupted its dynamo, scrambled the conducting fluid, and left the magnetic field in disarray. That was the thinking for decades. But then Voyager 2 reached Neptune, and Neptune's magnetic field turned out to be just as weird. Tilted 47 degrees from its rotation axis, offset from the planet's center by more than half the planet's radius. And Neptune was not tipped on its side. Neptune spins at a relatively normal angle, so the bizarre magnetic field could not be explained by the tilt alone. This suggested something deeper, something about the internal structure of ice giants themselves, something about the way water, ammonia, and methane behave under extreme pressure. Deep inside Uranus and Neptune, at depths of thousands of kilometers below the cloud tops, the pressure becomes so intense that the molecules that make up the planet's interior begin to behave in ways we do not see anywhere on Earth. Water, at pressures millions of times greater than what we experience at sea level, enters an exotic state called superionic ice. In this state, the oxygen atoms lock into a crystalline lattice, like a solid, while the hydrogen atoms flow freely through the lattice like a liquid. It is simultaneously solid and liquid, ice and not ice, a state of matter that exists nowhere on Earth naturally, but that may fill the interiors of billions of ice giant planets scattered across the galaxy. This superionic water is electrically conducting, and it is believed to be the fluid that drives the dynamo inside Uranus and Neptune. But unlike the metallic hydrogen inside Jupiter, which fills a massive spherical region deep inside the planet, the conducting layer inside an ice giant may be thinner, shallower, and arranged in a shell rather than a sphere, and a dynamo operating in a thin shell rather than a deep sphere naturally produces a magnetic field that is offset and tilted. In other words, the weird magnetic field of Uranus might not be a sign of damage. It might simply be what happens when you build a planet out of ice instead of gas. It might be the normal state of affairs for an ice giant, and we just did not know it because we had never looked closely at one before. But then came the twist. In 2024, researchers went back to the Voyager 2 data with fresh eyes and modern analytical tools. What they discovered added yet another layer of mystery. It turns out that Voyager 2 flew past Uranus during an extremely rare solar wind event. Just days before the flyby, a powerful burst of charged particles from the Sun slammed into the Uranian magnetosphere, compressing it dramatically. This solar wind event may have pushed plasma out of the magnetosphere and energized the radiation belts around Uranus, making them appear far more intense than they normally would be. For nearly 40 years, Scientists had looked at Uranus's magnetosphere and seen something that did not match their models. The radiation belts were too powerful. The plasma levels were too low. The whole system seemed to be operating under conditions that should have been impossible. And now there was an explanation. Voyager had caught Uranus during a storm. Not an atmospheric storm, but a magnetospheric one. A cosmic coincidence that may have distorted our understanding of the planet for 4 decades. Think about that for a moment. The only time we have ever visited Uranus, we happened to arrive during what may have been a once-in-20-year event. Everything we thought we knew about how the planet's magnetic environment works may have been shaped by that single stroke of bad luck, or good luck, depending on how you look at it, because the discovery of this coincidence has opened up entirely new questions about what Uranus is really like when nobody is looking. And that is the thing about Uranus. Every answer leads to another question. Every explanation peels back another layer of mystery. It is a planet that seems almost designed to resist understanding, but we are not done, not even close, because the strangeness of Uranus extends far beyond its interior. It extends outward, into the cold space around it, where a system of rings and moons tells a story so unusual that some scientists believe the entire system had to be rebuilt from scratch after whatever cataclysm reshaped the planet itself. Let us look up. Let us look at the rings. When you think of planetary rings, you probably think of Saturn. Bright, wide, spectacular, visible through even a modest telescope. Saturn's rings are the supermodel of the solar system, impossible to miss and impossible to forget. Uranus has rings too, but they are nothing like Saturn's. The rings of Uranus are dark, not just dark compared to Saturn's, but genuinely, profoundly dark. They reflect almost no light. Their albedo, the measure of how much light a surface reflects, is among the lowest of any material in the solar system. If Saturn's rings are made of gleaming ice, Uranus's rings appear to be made of something more like charcoal. Dark, carbon-rich particles, some as small as grains of sand and others as large as small boulders, orbiting the planet in thin, narrow bands that are almost invisible against the blackness of space. There are 13 known rings around Uranus. The inner 9 were discovered in 1977, not by a telescope pointed at the planet, but by accident. Astronomers were observing a star as Uranus passed in front of it, a technique called stellar occultation, hoping to study the planet's atmosphere. Instead, they noticed that the star blinked several times before Uranus itself blocked it, and several times after. The blinks were the rings, each one so thin and dark that they could only be detected by the brief shadow they cast on the light of a distant star. 2 more rings were found by Voyager 2 in 1986, and 2 more were discovered by the Hubble Space Telescope in 2003. The outermost ring is blue, similar in color to Saturn's faint E ring, which is fed by geysers erupting from the moon Enceladus. The rest are grey to reddish, and all of them are remarkably thin. But here is the question that haunts planetary scientists. Why are the rings so narrow? Why are they so dark? And how are they still there at all? Rings are not permanent features. They erode over time. Particles collide, lose energy, and either fall inward toward the planet or drift outward and disperse. Without something to replenish them, rings should fade and disappear over millions of years. Saturn's rings may be relatively young, perhaps only 100 million years old, constantly refreshed by material from the planet's moons. But Uranus's rings are thin and dark, and apparently ancient, and the question of what maintains them remains open. Some scientists believe the rings may be the shattered remains of moons that strayed too close to the planet and were ripped apart by tidal forces. Others think they are debris left over from the same giant impact that tipped Uranus on its side. Either way, the rings are a reminder that the space around Uranus is not empty. It is haunted by the ghosts of whatever came before. And speaking of ghosts, let us talk about the moons. Uranus has 28 known moons. Most of them are small, dark, and unremarkable, little more than captured asteroids or fragments of ancient collisions drifting in the planet's gravitational embrace. But 5 of them are large enough to be studied in some detail, and they are named not for the gods and heroes of Greek and Roman mythology, like the moons of every other planet, but for characters from the plays of William Shakespeare and the poems of Alexander Pope. There is Oberon, the outermost of the large moons, named for the king of the fairies in A Midsummer Night's Dream. There is Titania, the largest of the Uranian moons, named for Oberon's queen. There is Umbriel, dark and mysterious, named for a character in Alexander Pope's The Rape of the Lock. There is Ariel, the brightest of the group, named for a spirit in The Tempest. And then there is Miranda. Miranda is where the story gets truly strange. Named for the daughter of the sorcerer Prospero in Shakespeare's The Tempest, Miranda is the smallest and innermost of the 5 major moons. It is only about 480 kilometers across, roughly the distance from New York to Pittsburgh. By the standards of planetary satellites, it is tiny, and given its small size and extreme distance from the Sun, scientists expected it to be a frozen, cratered, geologically dead world, something like Saturn's moon Mimas, a ball of ice pockmarked with ancient impacts and utterly still. What Voyager 2 found instead was one of the most bizarre surfaces in the entire solar system. Miranda looks like it was assembled from spare parts. Its surface is a chaotic patchwork of wildly different terrains crammed together with no apparent logic. There are old, heavily cratered plains sitting right next to young, grooved regions full of ridges and valleys. There are strange oval formations called coronae, bright and dark bands arranged in chevron patterns, like giant racetracks carved into the ice. And there are cliffs, enormous cliffs. The tallest cliff on Miranda, a feature called Verona Rupes, is roughly 20 kilometers high. That is nearly 12 times the depth of the Grand Canyon. If you stood at the top of Verona Rupes and dropped a rock, it would take about 12 minutes to reach the bottom, falling in the weak gravity of this tiny frozen moon. How do you explain a world like this? How does a moon the size of a small country end up with a surface that looks like a geological jigsaw puzzle assembled by a toddler? One early theory was dramatic. Scientists proposed that Miranda had been shattered by a catastrophic impact, blown to pieces, and then reassembled by gravity. The fragments would have fallen back together randomly, with pieces of the original core ending up on the surface and pieces of the original surface buried deep inside. This would explain why the terrain looks so jumbled, why old and young regions sit side by side with sharp boundaries between them. Some researchers even suggested this might have happened more than once. Maybe Miranda was shattered and reassembled as many as 5 times over the course of its history, each collision scrambling the moon a little differently, each reassembly producing a slightly different patchwork of mismatched terrain. It is a dramatic idea. And while more recent research has offered alternative explanations, suggesting that the corona might be the result of tidal heating when Miranda was locked in an orbital resonance with another moon, or that they could be sites of massive meteorite impacts that partially melted the subsurface, the shattered moon hypothesis has never been completely ruled out. And here is why it matters. If Miranda was shattered by an impact, what did the impacting? The most likely answer is debris from the same event that tipped Uranus on its side. The giant impact that knocked Uranus over would have created an enormous cloud of debris orbiting the planet. That debris would have interacted with the existing moons, potentially disrupting their orbits, smashing some of them apart, and creating the conditions for new moons to form from the wreckage. In fact, some models suggest that the entire inner moon system of Uranus may have been destroyed and rebuilt after the giant impact. The moons we see today might not be the original moons at all. They might be second-generation satellites, born from the rubble of a cataclysm so violent it reshaped not just the planet, but everything around it. And just recently, in 2025, the James Webb Space Telescope discovered yet another tiny moon orbiting Uranus, bringing the total to 28. This new moon is only about 10 kilometers across, orbiting between the inner ring system and the known moons, so small and dark that Voyager 2 missed it entirely. Its nearly circular orbit suggests it may have formed near its current location, possibly from the same ancient debris that created the rings. Every new discovery around Uranus seems to deepen the mystery rather than resolve it. The planet and its moons are like a crime scene, where every piece of evidence raises more questions than it answers. Now, let us go deeper. Let us talk about what is happening inside the planet itself. Not the heat, not the magnetic field. Something even more remarkable. Let us talk about the rain. Deep inside Uranus, thousands of kilometers below the cloud tops, the conditions become almost unimaginable. The pressure climbs to millions of times the atmospheric pressure on Earth's surface. The temperature, despite the planet's frigid exterior, rises to thousands of degrees, and the materials that make up the planet's interior, water, methane, and ammonia, enter states of matter that have no equivalent on Earth. We already talked about superinic ice, where water becomes simultaneously solid and liquid. But methane does something even stranger. Under extreme pressure, the carbon and hydrogen atoms in methane molecules are forced apart. The hydrogen escapes upward, and the carbon, freed from its molecular bonds and compressed by the weight of the planet above it, crystallizes into diamond. This is not science fiction. This is not speculation. Laboratory experiments have confirmed that under the conditions found inside ice giants, carbon atoms can and do form diamonds. In 2017, researchers at the ESLAC National Accelerator Laboratory used high-powered lasers to recreate the temperatures and pressures found deep inside Uranus and Neptune. They compressed a plastic material made of carbon and hydrogen to pressures of 150 gigapascals and temperatures above 5,000 degrees Celsius. And they watched, in real time, as the carbon atoms rearranged themselves into tiny diamond crystals. More recent experiments, published in 2024, found that the presence of oxygen in the mix makes diamond formation even more likely, suggesting that diamonds could form at shallower depths and under a wider range of conditions than previously thought. Inside Uranus, these diamonds would not stay where they formed. They would be denser than the surrounding fluid, and gravity would pull them downward. Slowly, over thousands or millions of years, the diamonds would sink through the layers of hot, compressed ice, falling deeper and deeper into the planet's interior. It would be, quite literally, a rain of diamonds, falling through darkness, falling through pressures that would crush anything we have ever built, falling toward the center of a planet that no human will ever visit. And here is the twist. The sinking diamonds would generate friction as they fell through the surrounding medium. That friction would produce heat, which means the diamond rain might actually be one of the mechanisms that keeps the interior of Uranus warm. The planet's own jewels, falling endlessly inward, might be the slow-burning fuel of its internal furnace. Some researchers have even speculated that at the very center of Uranus, where the temperatures are highest and the pressures most extreme, the diamonds might accumulate in a thick layer around the rocky core. Others have suggested that if the temperatures are high enough, the diamonds might melt, forming an ocean of liquid carbon with enormous diamond icebergs floating on its surface. An ocean of liquid carbon, icebergs made of diamond, at the center of a planet that nobody pays attention to. It is enough to make you wonder what else is hiding in the places we have not bothered to look. But the diamonds are more than just a dazzling curiosity. They may hold the key to understanding one of the most puzzling features of Uranus and Neptune, their bizarre magnetic fields. Remember, the magnetic field of an ice giant is generated by electrically conducting fluids sloshing around in the planet's interior. Diamond rain falling through a layer of supersonic ice would stir that conducting fluid, creating currents and eddies that could influence the shape and orientation of the magnetic field. Recent research suggests that diamond rain forms above the layer of conducting ice, and as the diamonds sink, they drag gas and ice with them, entraining the surrounding material in their descent. This stirring effect could help explain why the magnetic fields of Uranus and Neptune are so tilted, so offset, so unlike anything we see at Jupiter or Saturn. The diamonds are not just pretty. They are part of the engine that makes the planet work. And now, let us pull back. Let us rise up out of the crushing depths of Uranus's interior, past the diamond rain, past the layers of exotic ice, past the thin atmosphere of hydrogen and helium and methane that gives the planet its pale blue-green color. Let us look at Uranus from the outside, the way Voyager 2 saw it for the first and only time. Because when Voyager got there, it found something unexpected. Or rather, it did not find something expected. It found nothing. Well, not nothing. It found a planet. But compared to Jupiter, with its roiling bands of clouds and its great red spot, or Saturn, with its hurricanes and hexagonal jet streams, or even Neptune, which Voyager would visit 3 years later and find surprisingly active and stormy, Uranus was featureless, bland, a smooth, pale blue-green ball with almost no visible atmospheric detail. This was confusing. Uranus is a giant planet with powerful winds. Its atmosphere is made of the same basic ingredients as the other giants. It should have storms. It should have bands. It should have something. But in 1986, when Voyager 2 arrived, it found a world that looked like someone had draped a bedsheet over it and called it a day. The explanation, scientists now believe, lies in the seasons. When Voyager arrived, Uranus was near its southern summer solstice. The South Pole had been pointed almost directly at the sun for years, bathing one hemisphere in continuous sunlight, while the other sat in darkness. This arrangement may have suppressed the normal atmospheric circulation patterns that create visible features on other giant planets. Without the typical contrast between sunlit and shadowed regions that drives weather on a normally tilted planet, Uranus appeared eerily calm. But the planet is not always so quiet. In 2004, nearly 2 decades after the Voyager flyby, large clouds began to appear in the Uranian atmosphere. Earth-based telescopes detected massive storm systems, including one persistent thunderstorm that researchers nicknamed the 4th of July fireworks. Wind speeds were measured at over 800 kilometers per hour. The seemingly dead planet was suddenly alive, churning with activity that had been invisible during the one and only time we had been close enough to see. And in the years since, as Uranus has continued its slow, 84-year orbit around the Sun, shifting from summer to autumn to approaching its equinox, more atmospheric features have appeared. Bright clouds, dark spots, bands of different composition revealing themselves at infrared wavelengths. Uranus is waking up, shedding its blank face, showing that beneath the featureless exterior there has always been a complex, dynamic atmosphere. We just happened to visit during the one season when it all went quiet. It is like visiting a city during a power outage and concluding that nobody lives there. The city was there all along. We just could not see it. Now, consider this. Everything we have learned about Uranus so far, every anomaly, every mystery, every piece of the puzzle, has been gathered from a distance of nearly 2 billion miles. The only close-up data we have is from a single flyby in 1986, a flyby that lasted mere hours, that caught the planet during an unusual magnetospheric event, during its most featureless seasonal phase, and that used instruments designed in the 1970s. We know more about the surface of Pluto thanks to the New Horizons mission in 2015 than we know about the interior of Uranus. We have more detailed maps of Jupiter's moons than we have of Miranda. We have studied Saturn's rings with the Cassini spacecraft for 13 years. We have orbited Mars and Venus and Mercury. We have landed on Titan and on comets and on asteroids. But Uranus has had one visitor. One time, 40 years ago, and everything we think we know is built on that single fleeting encounter. That is not a complete picture. That is a snapshot taken through a foggy window at night. And yet, despite how little we know, the planet keeps revealing surprises. The James Webb Space Telescope has begun to change things. Since its launch in 2021, Webb has turned its infrared eyes toward Uranus multiple times, revealing details that were invisible to every previous telescope. Webb has captured the planet's seasonal north polar cap, a bright, hazy region covering the pole that faces the Sun. It has revealed the faint inner rings with a clarity never seen from Earth orbit. And in early 2025, an international team used Webb's NEARSPEC instrument to map the vertical structure of Uranus's upper atmosphere for the first time. What they found was remarkable. They detected the faint glow of molecules high above the clouds and used it to map how temperature and charged particles vary with altitude across the planet. They found 2 bright auroral bands near the magnetic poles, regions where charged particles from the solar wind spiral down along the planet's magnetic field lines and excite atmospheric molecules, causing them to glow. And they found that Uranus's atmosphere has continued to cool over the past 3 decades, providing the most detailed portrait yet of how this ice giant distributes energy in its upper layers. These observations are opening a new chapter in our understanding of Uranus. But they are still observations from afar. What scientists really want is to go back, to send a dedicated orbiter and probe to Uranus, to study it up close for years, not hours, and the scientific community agrees. In 2022, the Planetary Science Decadal Survey, the document that sets priorities for NASA's planetary exploration program for the next decade, placed a Uranus orbiter and probe at the very top of its priority list, above a return to Venus, above a mission to Neptune, above everything. The scientific community looked at everything we do not know about Uranus and said, this is where we need to go next. Such a mission, if funded and built and launched, would take roughly 13 years to reach Uranus. it would carry instruments to study the planet's atmosphere, interior structure, magnetic field, rings, and moons in detail that Voyager 2 could never have achieved. It would answer questions that have lingered since 1986. It would rewrite textbooks. But missions like this are expensive. They compete for funding with other priorities. And the future of such a mission remains uncertain. The spacecraft does not yet exist. The instruments have not been built. The money has not been committed. Uranus sits in the dark, patient and silent, waiting for us to decide whether it is worth the journey. Let us think about what is at stake. Let us zoom out, past the rings and moons, past the planet itself, past our entire solar system. Let us look at the galaxy, because here is something that most people do not realize about Uranus. For decades, it was treated as an oddity, a misfit, the weird planet that nobody studied because it was too far away and too boring to bother with. But in the last 20 years, as our ability to detect planets around other stars has exploded, a stunning fact has emerged. Planets like Uranus may be the most common type of planet in the galaxy. When astronomers began cataloguing exoplanets using telescopes like Kepler and TESS, they expected to find solar systems that looked like ours. Big gas giants like Jupiter, small rocky worlds like Earth, maybe a few oddities here and there. What they found instead was a galaxy full of worlds that fell into a size range we had no example of in our own solar system. Worlds bigger than Earth but smaller than Neptune. Super-Earths and sub-Neptunes, planets roughly 2 to 4 times the radius of Earth, wrapped in thick hydrogen and helium atmospheres over cores of rock and ice. These sub-Neptunes are everywhere. They are, by a significant margin, the most common type of planet in the galaxy, and we have nothing like them orbiting our Sun. Our solar system has a gap between the rocky terrestrial planets and the ice giants, between Earth at 1 Earth radius and Neptune at 4 Earth radii. There is nothing. It is as if the universe decided to build billions of medium-sized planets, and our solar system forgot to include one. Now, whether these sub-Neptunes are truly scaled-down versions of Uranus and Neptune, or whether they are something fundamentally different, is still an active area of research. Recent studies using the James Webb Space Telescope suggest that many sub-Neptunes may be more like large rocky planets with thick atmospheres than like miniature ice giants. Their compositions may be quite different from Uranus, but the ice giant model remains crucial for understanding this class of planet. Uranus and Neptune are the closest analogues we have in our own solar system to the most common type of world in the galaxy. They are the Rosetta Stone that might help us decode billions of alien planets that we can only study as tiny dots of light crossing distant stars. And yet we know almost nothing about them. We have visited Uranus once. We have visited Neptune once. We have never orbited either one. We have never dropped a probe into the atmosphere of an ice giant. We have never measured the wind speeds, the chemical composition, the layered structure of these worlds with anything approaching the detail we have achieved at Jupiter and Saturn. This is, to put it gently, a significant gap in our knowledge of the universe. The most common type of planet in the galaxy, and our best examples of it, are the 2 least studied planets in our own solar system. It is like spending years studying houses and mansions and then discovering that most buildings in the world are actually 2-bedroom apartments, but you have never been inside one. Uranus is not the weirdo. Uranus might be the blueprint, and every year that we do not study it closely is another year that we remain ignorant of how the most common type of planet works, how it forms, how it evolves, and what it might be like to live on a world that big. Not that anyone could live on Uranus. There is no surface to stand on. The atmosphere simply gets thicker and denser the deeper you go, transitioning from gas to liquid to exotic states of matter without any clear boundary. The temperatures and pressures would crush and boil any spacecraft long before it reached the interior. The radiation environment is harsh. The magnetosphere is chaotic. It is, by any measure, one of the most hostile environments in the solar system. But that doesn't mean it has nothing to teach us. Hostile doesn't mean uninteresting. Hostile doesn't mean unimportant. Some of the most valuable lessons in science come from studying the places that are hardest to reach. And Uranus has been hard to reach in every sense. Physically, it is nearly 2 billion miles from Earth. Scientifically, it has resisted understanding at almost every turn. Culturally, it has been the butt of jokes for as long as most people can remember, its name providing endless ammunition for anyone who would rather laugh than learn. But the planet does not care about our jokes. It has been there for 4.5 billion years, spinning on its side in the dark, its diamond rain falling silently through layers of exotic ice, its magnetic field wobbling and twisting in ways that no one fully understands, its rings slowly fading, its moons carrying the scars of ancient violence. It does not need us to pay attention, but we need to pay attention to it, because Uranus is not just a planet. It is a question, a big, pale, blue-green question mark, hanging at the edge of everything we think we know about how worlds are made. Let us sit with that for a moment. Let us drift. Now, let us think about time, not human time, not the decades and centuries that measure the span of our civilizations, but planetary time, the deep, slow, patient time that Uranus has been keeping since the beginning. Uranus takes 84 Earth years to orbit the Sun once. That means a single year on Uranus, one complete trip around the star that gave it life, takes an entire human lifetime. A child born on Earth when Uranus was at one point in its orbit would be old and grey before the planet returned to that same point. And because of the extreme tilt, each season on Uranus lasts about 21 Earth years. 21 years of continuous sunlight at one pole. 21 years of unbroken darkness at the other. Then a slow, decades-long transition as the planet rolls over and the cycle begins again. Imagine living in perpetual daylight for 2 decades. Then imagine the sun slowly sliding toward the horizon, taking years to set, and then not rising again for another 2 decades. That is what the seasons are like on Uranus. Not the gentle oscillation of summer and winter that we experience on Earth, but vast, slow, epochal shifts between light and dark that play out over generations. We have only been watching Uranus with modern telescopes for about 2.5 of its years, 2.5 orbits. That is like studying the Earth's climate for a single weekend and trying to draw conclusions about what happens over centuries. We have barely scratched the surface of understanding how Uranus changes over the course of its own year, how its atmosphere responds to the slow march of its seasons, how the planet looks and behaves when it is in a part of its orbit that we have simply never observed. And this is important because the recent discovery of Uranus's internal heat showed us that the planet's energy budget changes with its seasons. The amount of sunlight it absorbs varies. The amount of heat it radiates varies. The balance between the two shifts over the course of its 84-year orbit. The Voyager flyby caught the planet at one point in that cycle. The recent observations from Hubble and Webb caught it at another. But we still do not have a complete picture. We are still guessing at the full shape of a process that takes nearly a century to complete. Patience is required. Cosmic patience. The kind of patience that planets have and humans typically do not. Now, let us go deeper into the atmosphere, because there are things happening in the upper layers of Uranus that deserve our attention, quiet things, subtle things, things that would be easy to miss if you were not looking carefully. First, the color. Uranus is blue-green, a soft, muted shade that is sometimes described as aquamarine or cyan. This color comes from methane in the upper atmosphere. Methane absorbs red light and reflects blue and green light back into space. The deeper the methane layer, the bluer the planet appears. Neptune is also blue, but a deeper, more vivid blue. This difference puzzled scientists for years because both planets have similar amounts of methane. The answer, discovered through careful, spectroscopic analysis, is that Uranus has a thicker layer of photochemical haze in its upper atmosphere. Sunlight hitting the methane and other hydrocarbons in the upper atmosphere triggers chemical reactions that create tiny particles of haze, a kind of smog that sits above the main cloud deck. This haze acts like a filter, muting the blue color and giving Uranus its distinctive pale, washed-out appearance. Neptune, despite being farther from the Sun and receiving even less light, has a thinner haze layer. This might be because Neptune's atmosphere is more active, with stronger vertical mixing that prevents the haze from building up. Or it might be related to differences in the internal heat, which drives convection and atmospheric circulation. Whatever the reason, Uranus appears paler than Neptune, and the haze is to blame. Below the haze layer, the atmosphere of Uranus is organized into bands, just like Jupiter and Saturn, but far more subtle. These bands are driven by the planet's rotation and by the differences in heating between the equator and the poles. On a normally tilted planet, the equator receives the most sunlight and the poles receive the least, creating a temperature gradient that drives atmospheric circulation from the equator toward the poles. But Uranus is not normally tilted. During its solstices, the pole facing the Sun receives more direct sunlight than the equator. This reverses the normal temperature gradient and creates atmospheric circulation patterns that are unlike anything found on any other planet. The winds on Uranus blow in the same east-west direction as on other giant planets, but the way those winds are driven and the way they change with the seasons is unique. Wind speeds on Uranus can reach over 900 kilometers per hour at some latitudes. These are not gentle breezes. These are sustained, relentless streams of gas howling through an atmosphere that has no surface to slow them down. On Earth, friction with the ground and with mountains and oceans dissipates wind energy. On Uranus, there is nothing but more atmosphere, all the way down, and the winds can build and persist for decades or longer. In the troposphere, the lowest layer of the atmosphere, the main clouds are thought to be made of hydrogen sulfide, the compound that gives rotten eggs their distinctive smell. Above that, there may be clouds of ammonia, and higher still, thin wisps of methane ice. But the exact structure of Uranus's cloud layers remains uncertain, because we have never sent a probe into the atmosphere to measure it directly. Everything we know comes from remote observations, from analyzing the light that bounces off the planet and passes through its atmosphere. And remote observations can only tell you so much. They can reveal what gases are present. They can estimate temperatures and pressures at certain altitudes, but they cannot tell you what it would be like to descend through those clouds, to feel the pressure build, to see the light fade from pale blue to darkness as you sink deeper and deeper into a world with no bottom. That is what a future Uranus probe could do. Drop through the atmosphere, measuring temperature, pressure, wind speed, and chemical composition all the way down. transmitting data for as long as its batteries and its structural integrity hold out, until the pressure crushes it, until the heat overwhelms it, until the planet swallows it whole and adds its atoms to the vast, churning interior. We sent probes like this into Jupiter's atmosphere. The Galileo probe survived for nearly an hour, transmitting data as it plunged to a depth where the pressure exceeded 23 times the atmospheric pressure on Earth's surface. A Uranus probe would face similar challenges, but in a very different environment. The chemical composition is different. The temperature profile is different. The pressure curve is different. Everything about an ice giant's atmosphere is different from a gas giant's, and we have never measured any of it directly. The questions are there. The technology is there. What we need is the will. Let us talk about lightning. Uranus has lightning. This might not seem remarkable. Many planets have lightning. Earth has lightning. Jupiter has lightning that dwarfs anything on Earth. Saturn has storms that generate radiostatic so powerful it can be detected from space. But Uranian lightning is particularly interesting because of what it tells us about the planet's atmosphere. Lightning requires convection. It requires updrafts and downdrafts, charged particles being separated by turbulent motion in the clouds, building up an electrical potential until it discharges in a flash. On Earth, this happens in thunderstorms. On Jupiter, it happens in the deep atmosphere where water clouds form. On Uranus, lightning tells us that despite the planet's apparently calm exterior, there is violent convective activity happening somewhere in the atmosphere. The clouds might look smooth from space, but deep down, they are churning. Voyager 2 detected lightning at Uranus, and interestingly, the signal was clearer than the lightning detected at Neptune. Scientists believe this might be because Uranus's lower gravity allows convection to proceed more vigorously in certain atmospheric layers, or because the deep atmosphere of Uranus is warmer than expected, providing more energy to drive thunderstorms. Lightning also has chemical consequences. The energy in a lightning bolt can break apart stable molecules and create new compounds. On Earth, lightning helps produce nitrogen compounds that are important for life. On Uranus, lightning may be driving chemical reactions in the deep atmosphere that create complex hydrocarbons and other compounds, adding to the already exotic chemistry of the planet's interior. We are only beginning to understand the atmospheric dynamics of Uranus. Every new observation, whether from ground-based telescopes, Hubble, Webb, or the occasional stellar occultation, adds another piece to a puzzle that is still mostly empty. The picture that is emerging is of a planet far more complex and dynamic than the bland, featureless world that Voyager 2 photographed in 1986. Uranus is not boring. It never was. We were just not looking closely enough. And now let us return to a theme that has been threading through this entire story. The theme of perspective. The theme of what we think we know versus what we actually know, versus what we cannot even begin to guess. Because here is the truth about Uranus, and it applies to the entire universe, but it applies to Uranus more than most places. We are working with almost no information. Our entire understanding of this planet is built on a foundation of a single flyby, a handful of photographs, some measurements from instruments designed half a century ago, and a collection of blurry telescope images gathered from nearly 2 billion miles away. From this thin gruel, we have constructed a story about a planet that was born normally, but struck by a catastrophic impact that tipped it on its side, scrambled its interior, bled away its heat, disrupted its magnetic field, shattered its moons, and left it rolling through the dark in a state of permanent dishevelment. It is a compelling story. It fits most of the evidence, and it might be completely wrong. Science is honest about this. The giant impact hypothesis is the leading theory, not the proven explanation. There are alternative models. Some researchers have proposed that Uranus could have been tipped gradually by a series of smaller impacts rather than one large one. Others have suggested that gravitational interactions during the chaotic early days of the solar system could have tilted the planet without any impact at all, through a process of resonant gravitational nudging over millions of years. And some of the things we attributed to the impact may have simpler explanations. The internal heat deficit, as we discussed, turns out to be less extreme than we thought. The weird magnetic field may be a normal feature of ice giants rather than a scar from ancient violence. The featureless atmosphere was a seasonal artifact, not a permanent condition. This does not mean the giant impact did not happen. It probably did. The extreme tilt is very hard to explain any other way. But the details, the what and when and how, remain frustratingly vague, and they will remain vague until we go back. The universe is under no obligation to make itself easy for us to understand, and Uranus, more than most objects, seems to revel in its own inscrutability. It sits at the edge of the solar system, barely visible to the naked eye, rotating in the wrong direction, tilted at an impossible angle, wrapped in a bland exterior that hides an interior of staggering complexity. It is a planet that rewards patience, and patience is something that science, at its best, has in abundance. Now let us think about something different. Let us think about beauty, because for all its strangeness, for all its puzzles and paradoxes, Uranus is beautiful. Not in the obvious way that Saturn is beautiful, with its gleaming rings catching the sunlight like a crown. Not in the dramatic way that Jupiter is beautiful, with its swirling storms painted in shades of orange and cream. Uranus is beautiful in a quieter way, a more subtle way. It is the beauty of distance, of cold, of solitude. Uranus is nearly 2 billion miles from the Sun. At that distance, the Sun appears as a bright star, still brighter than anything else in the sky, but no longer the blazing disk we see from Earth. The light that reaches Uranus is dim. The warmth is negligible. The planet orbits in a perpetual twilight, lit enough to see, but not enough to feel. And it has been doing this for 4.5 billion years, alone, patient, turning slowly on its side in the cold. There is something about that image that touches something deep in the human experience. We know what it is to feel alone. We know what it is to feel different. We know what it is to carry scars that nobody else can see. And Uranus, for all its inhuman scale and alien composition, carries all of these qualities. A planet that was struck so hard it fell over and never got back up. A planet that lost most of its warmth in the aftermath of that blow and has been slowly, silently cooling ever since. A planet whose moons bear the evidence of that ancient violence in their fractured surfaces and chaotic terrains. A planet that, when we finally got close enough to look at it, appeared to have nothing going on, only for us to realize, decades later, that we had simply visited at the wrong time. There is poetry in that. Not the poetry of triumph or discovery, but the quieter poetry of endurance, of carrying on, of spinning in the dark regardless of what has happened to you. And perhaps that is why, despite the jokes and the neglect and the decades of indifference, Uranus has begun to capture the imagination of scientists and the public alike. Because in Uranus, we see a reflection, not of ourselves exactly, but of the parts of the universe that are messy and broken and mysterious and still, somehow, beautiful. The more we learn about the cosmos, the more we realize that the universe is not a tidy place. Planets do not always form the way they should. Moons get shattered and reassembled. Magnetic fields tilt and wobble. Diamond rain falls through oceans of exotic ice. And the most common type of planet in the galaxy is one that we have barely studied. These are not problems to be solved and filed away. They are invitations. Invitations to look more closely, to ask better questions, to build the spacecraft and the telescopes and the computer models that will let us peel back the layers of mystery one at a time. Uranus has been waiting for us for 4 billion years. It can wait a little longer, but we probably should not. Let us drift a little further now. Let us think about Uranus in the context of its siblings. Because to fully appreciate how strange Uranus is, it helps to compare it to the planet it most resembles and yet most profoundly differs from, Neptune. Uranus and Neptune are often described as twins, and in some ways they are. They are similar in size, with Uranus having a diameter of about 51,000 kilometers and Neptune about 49,000. They are similar in mass, with Uranus at roughly 14.5 Earth masses and Neptune at about 17. They are both ice giants, built from the same basic materials of water, methane and ammonia, over cores of rock and metal. They are the only 2 planets of their type in our solar system. But the similarities end there. Neptune is hot inside. It radiates more than 2.5 times as much energy as it receives from the sun. Its internal furnace is roaring. Uranus, as we discussed, barely glows. Neptune has a dynamic, active atmosphere, full of storms and bands and the occasionally recurring great dark spot, a vortex reminiscent of Jupiter's great red spot. Uranus, for most of the time we have been watching it, has appeared calm and featureless, only recently beginning to show signs of activity as its seasons shift. Neptune's largest moon, Triton, orbits in the wrong direction, retrograde, suggesting it was captured from the Kyper belt. Uranus's large moons all orbit in the same direction as the planet's rotation, in the planet's equatorial plane, suggesting they formed in place, possibly from the same disk of debris created by the giant impact. And perhaps most intriguing, Neptune's magnetic field, while also tilted and offset, operates in a planet that is not tipped on its side. Neptune rotates at a relatively normal 28-degree tilt. This means whatever is causing the bizarre magnetic fields in ice giants is not related to axial tilt at all. It is something fundamental about the way these planets are built. This comparison tells us something important. Uranus and Neptune started from similar raw materials, but their histories diverged dramatically. Something happened to Uranus that did not happen to Neptune, or perhaps something happened to Neptune that did not happen to Uranus. The giant impact hypothesis explains many of the differences, but not all of them. And until we can study both planets in detail, we will never fully understand either one. It is like trying to understand human nature by studying only one person. You need the comparison. You need the contrast. You need to see how the same ingredients can produce different outcomes under different circumstances. Uranus and Neptune together are a natural experiment, a controlled test of how ice giants develop when their histories differ. And right now, we are trying to read the results of that experiment with one eye closed and the other one squinting through a telescope from very, very far away. Let us continue to drift. Let us think about what happens next. Not next in the story of Uranus, because that story will unfold on its own, whether we are watching or not, but next in our story, the story of human curiosity, the story of exploration. The Uranus orbiter and probe, if it is ever built, would be a flagship-class mission, one of the most ambitious planetary science endeavors in NASA's history. It would launch sometime in the early to mid-2030s, take advantage of a gravitational assist from Jupiter, and arrive at Uranus roughly 13 years later, sometime in the mid to late 2040s. Think about that timeline for a moment. A child born today would be in high school or college by the time the spacecraft launched. They would be approaching middle age by the time it arrived. The patience required for outer solar system exploration is not measured in weeks or months. It is measured in decades, in careers, in lifetimes. And even that ambitious timeline is not guaranteed. Flagship missions cost billions of dollars. They require sustained political will, consistent funding, and a community of scientists and engineers who are willing to dedicate years of their professional lives to a project that may not bear fruit until they are near retirement. But the scientists who study Uranus are patient people. They have to be. They have spent their entire careers working with data from a single flyby that happened before many of them were born. They have squeezed every last drop of information from those Voyager 2 images and measurements. They have used ground-based telescopes, Hubble, and now Webb to fill in the gaps. And they have been advocating, passionately and persistently, for a return to the ice giants. Because they know what is at stake. Not just the answers to specific questions about Uranus's interior or magnetic field or moons, but the broader understanding of how planets work, how solar systems form, how the universe assembles its most common building blocks. These are not niche questions. They are fundamental questions about our place in the cosmos, and Uranus holds many of the answers. Let us now think about something that scientists rarely discuss in their papers, but that anyone who has ever looked up at the night sky knows instinctively. The feeling you get when you contemplate something truly vast and truly unknown. Uranus is out there right now, as you listen to these words. It is rolling through the dark at the edge of the solar system, its rings nearly invisible, its moons orbiting silently, its magnetic field wobbling and twisting through the void. Deep inside it, diamonds may be falling through oceans of exotic ice. Its atmosphere is shifting, slowly, as the seasons turn, and somewhere on its surface, there is a place where the sunlight is just beginning to return after 21 years of darkness. Nobody is watching. No spacecraft is monitoring it. No instrument is measuring the temperature of its atmosphere or the strength of its magnetic field or the chemical composition of its clouds. Right now, at this very moment, Uranus is entirely alone, and yet it goes on. The winds blow, the diamonds fall, the magnetic field churns, the planet rolls on its side, the same way it has for 4 billion years, carrying the scars of an ancient impact that no one witnessed, generating a feeble but persistent warmth that took us 4 decades to detect, harboring an entire system of moons and rings that may have been destroyed and rebuilt more than once. It goes on because the universe does not require an audience. It runs its experiments whether we are watching or not. The atoms do not care. The gravity does not care. The pressure and the temperature and the exotic states of matter that exist in the crushing depths of an ice giant's interior do not pause to see if anyone is paying attention. But we care. We care because we are the kind of creatures who look up at the sky and wonder, who build telescopes and spacecraft and send them billions of miles to photograph a planet that most people cannot even find in the night sky, who spend decades analyzing data from a single flyby, hoping to wring one more secret from a world that seems determined to keep them all. That caring is what makes us human, and that curiosity is what will eventually take us back to Uranus. Maybe not soon, Maybe not in our lifetimes, but eventually, because the questions are too good to leave unanswered. And the planet is too strange to ignore. Let us drift further still. The night is long, the universe is vast, and there is so much more to see. Think about what the James Webb Space Telescope has already shown us. In its observations of Uranus, Webb revealed auroras, glowing bands of light near the magnetic poles, where charged particles from the solar wind collide with atmospheric molecules. On Earth, we know these as the northern and southern lights, shimmering, curtains of green and red and purple that dance across the sky near the poles. On Uranus, the auroras are different. They are infrared, invisible to the human eye, detectable only by instruments sensitive to wavelengths of light that our biology cannot perceive. And because Uranus's magnetic field is tilted so far from its rotation axis, the auroras do not appear at the geographic poles. They appear at the magnetic poles, which are offset and tilted, which means the auroras sweep across the planet's surface as it rotates, tracing out complex patterns that shift and change over the course of each 17-hour day. In January 2025, Webb's NIRSpec instrument captured these auroras in unprecedented detail, mapping how they vary with altitude and across the planet's surface. The observations revealed two distinct auroral bands, regions of enhanced emission near each magnetic pole, along with a zone of reduced emission between them. This pattern tells scientists about the shape of Uranus's magnetic field at high altitudes, about how charged particles are funneled and accelerated along the field lines, about the energy budget of the upper atmosphere. But here is what struck the researchers most. The observations showed that Uranus's upper atmosphere has been cooling steadily over the past 3 decades. This is not what you would expect if the planet were simply sitting in space, absorbing sunlight and radiating heat. Something else is going on. Energy is being redistributed within the atmosphere in ways that are not yet fully understood. The auroras may play a role, depositing energy in the upper atmosphere through particle bombardment. Gravity waves, not gravitational waves, but oscillations in the atmosphere driven by convection from below, may be carrying energy upward and distributing it across the planet. These are the kinds of processes that we understand well on Earth and Jupiter, but have never been able to study on an ice giant. Each new observation from Webb adds another piece to the puzzle, but also reveals how many pieces are still missing. And there is something profound about that. About the fact that even with the most powerful space telescope ever built, we are still scratching the surface of Uranus. The planet has layers upon layers of mystery, each one deeper and more complex than the last. Every time we think we understand something, we find another question hiding behind it. This is not frustrating. Not really. This is what science is for. The joy is not in the answers alone. The joy is in the process, in the slow, patient accumulation of knowledge, each piece fitting imperfectly with the last, the picture gradually coming into focus over decades and centuries. Uranus has been teaching us patience since 1781, when William Herschel first spotted it through his homemade telescope and thought it was a comet. It took 2 years for the scientific community to accept that it was a planet. It took nearly 2 centuries before anyone got close enough to photograph it, and it will probably take another century before we truly understand it. But that is all right. The planet is not going anywhere, and neither, we hope, is our curiosity. Let us now think about names, because names matter, and the naming of Uranus tells us something about the planet and about ourselves. When Herschel discovered the 7th planet in 1781, he wanted to name it Georgium Sidus, George's star, after King George III of England. This was, to put it diplomatically, not a popular choice among non-British astronomers. The French suggested the name Herschel, after the discoverer himself, but eventually the German astronomer Johann Elert Bode proposed the name Uranus, after the ancient Greek god of the sky. In Greek mythology, Uranus was the primordial deity who personified the heavens. He was the father of the Titans, the grandfather of the Olympian gods, and one of the oldest entities in the Greek creation story. The sky itself, arching over the earth, holding the stars in place. It is a fitting name for a planet that sits at the boundary between the known and the unknown, between the visible and the invisible, between the planets that ancient civilizations could see with their naked eyes and the vast, dark realm beyond. Uranus was the first planet discovered with a telescope, the first world that required technology to find. In a very real sense, it marks the beginning of modern astronomy, the moment when we realized that the solar system was bigger than we thought. And now, 2.5 centuries later, it continues to mark the boundary of our knowledge, the edge of what we understand, the beginning of what we do not. The ancient Greeks believed that Uranus, the sky, was so vast and so ancient that it predated even the gods. It was there before everything else, watching, waiting, holding the universe together. The planet that bears that name carries some of the same qualities. It is ancient, it is vast. It watches and waits while we struggle to understand it, and it holds together mysteries that we are only beginning to unravel. Let us drift a little more. Imagine you are falling, not on Earth, where gravity pulls you down at a brisk 9.8 meters per second squared, but on Uranus, where the gravitational acceleration at the cloud tops is about 8.7 meters per second squared, slightly less than Earth's. But you would not be falling through air. You would be falling through hydrogen and helium, mixed with traces of methane that give the planet its color. The atmosphere would be thin at first, almost nothing, and incredibly cold. Temperatures at the cloud tops hover around negative 224 degrees Celsius, colder than liquid nitrogen. The wind would be a constant companion, pushing you sideways at hundreds of kilometers per hour, even as you fell downward. As you descended, the atmosphere would thicken, the pressure would rise, the temperature would climb. The pale blue light filtering down from above would fade to a deep indigo, then to purple, then to black. Within a few hundred kilometers of descent, you would be in total darkness, falling blind through an atmosphere that grows hotter and denser with every passing moment. At some point, you would pass through the cloud layers. First, the methane ice clouds, high and thin, then the hydrogen sulfide clouds, giving the air a smell that you would never actually experience because the pressure at that depth would have already crushed any human body. Then deeper still, through layers where ammonia and water might form their own cloud systems, hidden from all telescopes, never observed, only theorized. Deeper. The pressure is now thousands of times what you would feel at sea level on Earth. The temperature has climbed past the point where the hydrogen and helium that made up the upper atmosphere have given way to the heavier compounds that fill the interior. Water, ammonia, and methane in a state that is not gas, not liquid, not solid, but something else. A hot, dense, electrically conducting fluid. The material that drives the planet's magnetic field. Deeper still. The pressure exceeds millions of atmospheres. This is where the diamond rain happens. Carbon atoms, stripped from methane molecules by the crushing force, crystallize and begin their long, slow descent toward the center. You cannot see them. There is no light. But if you could somehow perceive what was happening around you, you would see countless tiny points of crystal forming, glinting in the darkness, if there were any light to glint, and then falling, silently, endlessly, through an ocean of material that defies easy description. And at the very center, roughly 13,000 kilometers below the cloud tops, there is the core, small, dense, rocky, perhaps the size of Earth but far heavier, compressed under the weight of the entire planet. The temperature here may reach 5,000 degrees Celsius. The pressure is around 8 million times the atmospheric pressure on Earth's surface. It is a hellish, unreachable place, the hidden heart of a planet that shows the universe nothing but a smooth, pale face. Nobody will ever see the core of Uranus. No probe will ever survive the descent. No instrument will ever directly measure the conditions there. Everything we know about it comes from models, from calculations, from indirect measurements of the planet's gravitational field and the way it responds to the motions of its moons. But knowing that it is there, that at the center of this quiet, tilted, seemingly featureless planet, there is a furnace of rock and metal, surrounded by diamond rain, wrapped in exotic ice, generating a magnetic field that wobbles drunkenly through the void. That knowledge changes the way you think about the planet. It changes the way you think about the universe, because the universe is like that. The most interesting things are often hidden. The most beautiful things are often invisible. And the most important questions are often the ones that nobody thinks to ask, because the planet seems so boring from the outside. Nothing is boring when you look closely enough. Not a single thing in this universe. And Uranus proves it. But before we think about endings, let us think about something else. Let us think about what it means to be an ice giant. Because that phrase, ice giant, is one of those terms that sounds straightforward, but hides a universe of complexity. When scientists talk about ice giants, they do not mean planets made of ice in the way you might picture ice cubes floating in a glass. The word ice in planetary science has a very specific meaning. It refers to volatile compounds, chemicals with relatively low freezing points, like water, ammonia, and methane. These are the building blocks of Uranus and Neptune, the stuff that makes them fundamentally different from the gas giants Jupiter and Saturn. Jupiter and Saturn are more than 90% hydrogen and helium by mass. They are essentially failed stars, balls of the lightest elements in the universe, compressed under their own gravity into worlds with no solid surface and no clear boundary between atmosphere and interior. They are gas through and through. Uranus and Neptune are different. They are only about 20% hydrogen and helium. The rest is heavier stuff: water, methane, ammonia, and other compounds that were solid or liquid when the planets formed but exist in exotic, unrecognizable states under the extreme pressures of the planetary interior. The word ice is a legacy of the fact that these compounds are typically found frozen in the cold outer solar system. But inside Uranus, nothing is frozen. Everything is hot. Everything is compressed. Everything is strange. The three-layer model of Uranus goes something like this. At the center, there is a small, dense core of rock and metal, perhaps half an Earth, mass, perhaps a bit more. Surrounding that core is the mantle, a vast ocean of hot, dense fluid made of water, ammonia, and methane. This mantle accounts for most of the planet's mass, roughly 13.5 Earth masses of material compressed to a density several times that of water. And above the mantle, there is the atmosphere, a relatively thin layer of hydrogen and helium that extends for the outermost 20% of the planet's radius. But this three-layer model is almost certainly too simple. The boundaries between layers may not be sharp. The composition may vary gradually, blending from one layer to the next without any clear dividing line. And the dynamics, the way material moves and mixes within the interior, are almost completely unknown. Does the interior of Uranus convect? That is, does hot material rise and cool material sink, creating circulation patterns that transport heat from the deep interior to the surface? On Jupiter and Saturn, the answer is clearly yes. Convection is vigorous, and it drives the powerful weather systems we see in their atmospheres. On Uranus, the answer is less clear. The early models, based on the Voyager data, suggested that Uranus might have a non-convective interior, a planet where the layers are stable, where hot material does not rise because the chemical composition changes with depth in a way that prevents mixing. If you have ever poured oil on water and watched them separate into distinct layers, you have seen a crude analogy for what might be happening inside Uranus. The interior might be stratified, with each layer sitting quietly on top of the one below it, preventing heat from escaping efficiently. This would explain the low internal heat. If the interior cannot convect, the heat is trapped, not missing, but locked away, unable to reach the surface. The planet would be hot inside but cold outside, like a thermos full of coffee sitting in a snowbank. But more recent models have complicated this picture. Some researchers have shown that with updated equations of state, which describe how materials behave under extreme pressure, a fully convective interior can actually be consistent with the observed luminosity of Uranus. In other words, the planet might be convecting normally and simply cooling faster than anyone expected. The truth is probably somewhere in between. Uranus's interior may have regions that convect and regions that do not. The boundaries between these regions may shift over time, and the whole system may be far more dynamic than we have given it credit for. This matters because the interior structure determines almost everything about the planet: the magnetic field, the heat budget, the atmospheric dynamics, the composition of the clouds, the fate of the diamond rain. If we do not understand the interior, we do not understand Uranus, period. And right now, we do not understand the interior. Let us explore another mystery, a small one perhaps, compared to the great puzzles of the tilt and the heat and the magnetic field, but a mystery nonetheless. Uranus smells terrible. That is not a joke, or rather, it is a fact that sounds like a joke. The upper clouds of Uranus are made primarily of hydrogen sulfide, the compound responsible for the stench of rotten eggs. Scientists confirmed this in 2018, using observations from the Gemini North Telescope in Hawaii, detecting the spectral signature of hydrogen sulfide in the planet's cloud tops. This is actually significant because Jupiter and Saturn have clouds made primarily of ammonia. The difference tells us something about the temperatures and chemical processes in the atmospheres of ice giants versus gas giants. At the cold temperatures found in Uranus's upper atmosphere, hydrogen sulfide condenses before ammonia does. So hydrogen sulfide clouds form at higher altitudes and dominate the visible cloud deck. On Jupiter, which is warmer, ammonia condenses first. It is a small detail. But in planetary science, small details often unlock big insights. The composition of the cloud deck tells us about the planet's overall chemical makeup, which tells us about how and where it formed, which tells us about the history of the entire solar system. If you could somehow take a deep breath on Uranus, which you could not because the atmosphere would kill you in dozens of ways before the smell became relevant, you would detect a powerful odor of rotten eggs mixed with the metallic taste of hydrogen and the faint, almost sweet scent of methane. It would be the worst breath of air in the solar system, taken on a planet where the wind is blowing at hundreds of kilometers per hour and the temperature is hundreds of degrees below zero. Some planets are glamorous. Uranus is the planet that smells like eggs. But even in its indignity, there is science, and the science matters. Let us now talk about something that connects all of this together. The question of water. Water is, in many ways, the key to understanding ice giants. Uranus and Neptune are called ice giants specifically because they contain so much of it. The water in their interiors is not the familiar liquid water that fills our oceans or the solid ice that caps our poles. It is water under conditions so extreme that it transforms into something almost unrecognizable. At pressures above about 50 gigapascals and temperatures above about 2000 degrees Celsius, water enters the supersonic state we discussed earlier. The oxygen atoms form a solid crystal lattice, while the hydrogen atoms flow through it like a liquid. This supersonic water is electrically conducting, which means it can carry currents and generate magnetic fields. It is also incredibly dense, denser than any form of water found naturally on Earth. Some models suggest that Uranus may contain a vast ocean of this supersonic water, extending from a depth of a few thousand kilometers all the way down to the rocky core. This ocean would not be a calm, placid body of liquid like an earthly sea. It would be a turbulent, churning mass of exotic material, heated from below by the core and cooled from above by the lighter atmosphere. And it would be the engine that drives the planet's magnetic field. But there is a problem. If the supersonic water ocean is what generates the magnetic field, and if the ocean is relatively thin compared to the planet's overall size, then the dynamo that produces the field operates differently from the dynamos in Jupiter and Saturn. A thin-shell dynamo, as it is called, naturally produces a magnetic field that is more complex, more variable, and more tilted than the simple dipole fields we see at the gas giants. This matches what we observe at Uranus and Neptune, but the details are still fuzzy. We do not know exactly how thick the conducting layer is. We do not know its precise composition. We do not know how it interacts with the layers above and below it. We do not know whether it convects, and if so, how vigorously. These are all things that a dedicated Uranus orbiter could help answer, using careful measurements of the planet's gravitational field and magnetic field over an extended period. Water also plays a role in the diamond rain. Recent experiments suggest that in the presence of water, diamond formation happens at lower pressures and temperatures than in a pure methane environment. This means the diamond rain zone inside Uranus may extend closer to the surface than originally thought, potentially overlapping with the supersonic water layer in ways that influence both the diamond formation process and the magnetic field dynamics. It is all connected. The water, the diamonds, the magnetic field, the heat. Every piece of the puzzle connects to every other piece, and understanding any one of them requires understanding all of them. This is what makes Uranus such a compelling target for exploration. It is not one mystery. It is a web of mysteries, interlocking and interdependent, each one shedding light on the others. Solve the heat puzzle, and you learn about the interior structure. Understand the interior structure, and you learn about the magnetic field. Map the magnetic field, and you learn about the conducting layer. Study the conducting layer, and you learn about diamond rain. Trace the diamond rain, and you learn about the heat budget. The circle closes, and at the center of the circle sits Uranus, quietly keeping all of its secrets at once. Let us now explore one more thread. The thread of habitability. Not on Uranus itself, which is emphatically not habitable, but on its moons. Because here is something that planetary scientists are increasingly excited about. Some of the moons of Uranus might harbor liquid water beneath their surfaces. This idea comes from the same revolution in planetary science that made Europa and Enceladus such tantalizing targets. We used to think that liquid water could only exist in the habitable zone, that narrow band around a star where temperatures are just right. But the discovery of tidal heating showed us that moons far from the habitable zone can maintain liquid water internally, heated not by the sun, but by the gravitational squeezing of their parent planet. Uranus's 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are all roughly half water ice and half rock. They are cold, they are small, they are far from the sun. And yet, models suggest that at least some of them, particularly Ariel and Titania, may have retained enough internal heat to maintain subsurface oceans of liquid water. The evidence is indirect. We have no direct measurements of the internal structures of these moons, but computer models of their thermal evolution, taking into account radiogenic heating from the decay of radioactive elements in their rocky interiors, tidal heating from gravitational interactions with Uranus and each other, and the insulating properties of their ice mantles, suggest that liquid water is plausible. In 2024, researchers published new geological mapping of Miranda's southern hemisphere, comparing the observed surface features to models of internal geological processes. Their work suggested that Miranda's complex surface might have been shaped by a combination of tidal heating and internal differentiation, processes that require significant amounts of heat. If Miranda, the smallest of the 5 major moons, could generate that much heat, then the larger moons, Ariel and Titania, with their greater mass and greater potential for radiogenic heating, could maintain subsurface oceans that persist to the present day. This is speculative. We do not know for certain that any Uranian moon has a subsurface ocean, but the possibility is there, and it is one of the most exciting aspects of a potential Uranus mission. A spacecraft in orbit around Uranus could measure the gravitational fields and magnetic signatures of these moons, looking for the telltale signs of a liquid water layer beneath the ice. It could image their surfaces at high resolution, mapping geological features that hint at internal activity. It could even detect plumes of water vapor or ice particles erupting from the surface, similar to the geysers found on Enceladus. If any of these moons turn out to harbor a subsurface ocean, it would expand the list of potentially habitable worlds in our solar system. Not habitable for humans, obviously, but habitable in the sense that the basic conditions for life as we know it, liquid water, a source of energy, and the right chemistry, might all be present. And that would be a profound discovery, not because we expect to find fish swimming beneath the ice of Ariel, but because it would mean that the conditions for life are even more widespread in the universe than we already thought. If a moon orbiting a planet nearly 2 billion miles from the Sun can maintain liquid water, then the number of potentially habitable worlds in the galaxy becomes almost incomprehensibly large. Uranus, the neglected planet, might be harboring one of the most important discoveries in the history of science, quietly, silently, in the dark. Now let us think about Verona Rupes. We mentioned it briefly when we talked about Miranda, but it deserves its own moment, because Verona Rupes is one of the most dramatic landforms in the entire solar system. Named after the setting of Shakespeare's Romeo and Juliet, Verona Rupes is a cliff on Miranda that rises roughly 20 kilometers above the surrounding terrain. 20 kilometers. To put that in perspective, Mount Everest is about 9 kilometers above sea level. The walls of the Grand Canyon are about 1.5 kilometers high. Verona Rupes is more than twice the height of Everest, on a moon that is less than 500 kilometers across. If you stood at the top of Verona Rupes and looked down, you would see a sheer drop that extended so far below you that the bottom would be lost in the curvature of the moon. The cliff face would stretch away on either side, a vast wall of ice and rock that defies any earthly comparison. And if you jumped, you would not die quickly. Miranda's surface gravity is only about 1/50th of Earth's. A jump from the top of Verona Rupes would take approximately 12 minutes to reach the bottom. You would fall in slow motion, accelerating gently, the cliff face drifting past you with an almost dreamlike quality. The experience would be nothing like falling on Earth. No rush of wind, no terminal velocity. Just a long, slow descent through a thin, near-vacuum atmosphere, with the pale, distant sun hanging in a black sky. At the bottom, you would hit at a speed of roughly 200 kilometers per hour, fast enough to be lethal even in weak gravity. But the fall itself would be almost serene. 12 minutes of free fall past a cliff that should not exist on a moon this small. How did Verona Rupes form? The honest answer is that we do not know. It might be a normal fault scarp, created by the tectonic activity that shaped Miranda's coronae. It might be the remnant of one of the hypothesized impact and reassembly events that gave Miranda its chaotic surface. It might be something entirely unexpected, a geological process that we have not identified because we have never seen anything like it elsewhere. We photographed Verona Rupes only once. Voyager 2, passing Miranda at a distance of about 29,000 kilometers, captured the images that revealed this astonishing feature. And then it was gone, hurtling onward toward Neptune, leaving Miranda behind with all its mysteries intact. 40 years later, those photographs are still the best we have. The highest resolution images of the tallest cliff in the solar system were taken with a camera designed in the 1970s, from a spacecraft that was moving at tens of thousands of kilometers per hour. Imagine what we could see with modern instruments. Imagine an orbiter carrying cameras with resolution 10 or 100 times better than Voyager's, making multiple passes over Miranda at close range, mapping every crack and ridge and grooved band in exquisite detail. Imagine a spectrometer analyzing the composition of the cliff face, determining whether the exposed material is pure water ice or a mixture of ice and rock and organic compounds. Imagine the discoveries waiting on that tiny, tortured moon. We know almost nothing about Miranda. We know almost nothing about any of Uranus's moons. And every piece of information we do have comes from a single, brief encounter that took place before the internet existed. The frustration of knowing just enough to know how much we are missing is one of the defining emotions of planetary science, and it is particularly acute when it comes to Uranus. Let us drift a little more. Let us think about something that astronomers rarely discuss in public, but think about constantly in private. The problem of analogy, Tao. When we try to explain Uranus to someone who has never studied planetary science, we reach for comparisons. We say the planet is like a bowling ball rolling on its side. We say the interior is like a thermos full of hot fluid. We say the diamond rain is like snowfall, only made of gemstones. We say the magnetic field is like a bar magnet shoved off-center inside a ball. These analogies are useful. They make the unfamiliar accessible. But they are also dangerous because they tempt us into thinking we understand something when we really do not. Uranus is not like a bowling ball. It is a gaseous, fluid world with no solid surface, spinning in a gravitational field shaped by its own mass and the distant pull of the Sun. The interior is not like a thermos. It is a realm of pressures and temperatures that do not exist anywhere on Earth, filled with materials in states that we can only briefly recreate in laboratories using the most powerful lasers ever built. The diamond rain is not like snowfall. It is a phase transition of carbon occurring at pressures millions of times greater than anything a human has ever experienced, in a medium that is simultaneously fluid and crystalline, at temperatures that would vaporize steel, and the magnetic field is not like a bar magnet. It is a complex dynamic phenomenon generated by currents flowing through an exotic ocean of superionic water, shaped by forces that we can model mathematically but cannot truly visualize. The gap between analogy and reality is vast. And with Uranus, that gap is wider than with almost any other object in the solar system, because Uranus is so fundamentally different from anything in our daily experience that our best metaphors barely scratch the surface. This is not a failure of communication. It is a feature of the universe. Some things are genuinely beyond analogy. Some realities can only be approached through mathematics and measurement, through the patient accumulation of data points that gradually build an understanding too complex for any single metaphor to capture. And that is part of what makes Uranus so fascinating. It resists simplification. It refuses to be reduced to a soundbite or a fun fact. Every time you think you have a handle on it, it reveals another layer of complexity that sends you back to the drawing board. That is not frustrating. That is exhilarating. That is the feeling of being in the presence of something genuinely new, something that our minds were not built to understand intuitively, but that our science allows us to approach one careful step at a time. Let us think now about discovery itself, about the moment of realization, about what it must have been like for the scientists who first understood how strange Uranus truly is. When Voyager 2 arrived at Uranus in January of 1986, expectations were modest. The spacecraft had already completed triumphant encounters with Jupiter in 1979 and Saturn in 1981, sending back images that transformed our understanding of both planets and their moons. Uranus was the third stop on a grand tour of the outer solar system, and most scientists expected it to be the least exciting. They were wrong, but in a peculiar way. Uranus was not exciting in the way Jupiter was exciting, with its roiling storms and volcanic moons. It was not exciting in the way Saturn was exciting, with its spectacular rings and the mysterious orange haze of Titan. Uranus was exciting because it was confusing, because everything about it seemed wrong. The magnetic field was tilted and offset. The heat was missing. The atmosphere was blank. The rings were dark and impossibly thin. And Miranda, tiny Miranda, looked like it had been assembled by committee using spare parts from 5 different moons. The Voyager team had expected Miranda to look like Mimas, Saturn's small, cratered, geologically dead moon. They had 24 hours between receiving the images and releasing them to the press. And in those 24 hours, they scrambled to come up with explanations for features that no one had predicted and no existing model could account for. That scramble, that moment of beautiful confusion, is one of the purest expressions of scientific discovery. The moment when the data defies your expectations, when the universe tells you that your theories are incomplete, when you realize, with a mixture of frustration and delight, that you have been wrong about something, and being wrong means there is something new to learn. That feeling has defined Uranus science for 4 decades. Every new observation, every new model, every new paper has been an attempt to reconcile what we expected with what we found, and the reconciliation is still ongoing. Consider the Voyager team's experience with the magnetic field. They had models, they had predictions. They expected Uranus's magnetic field to behave like a scaled-down version of Saturn's, roughly aligned with the rotation axis, roughly dipolar, roughly symmetrical. What they found instead was a field tilted 60 degrees, offset by 1/3 of the planet's radius, and wildly asymmetrical. The initial reaction was that the impact must have done it. The same impact that tipped the planet over must have disrupted the interior and scrambled the magnetic field. It was a reasonable hypothesis. But then Voyager reached Neptune 3 years later and found an equally bizarre magnetic field on a planet that was not tipped over at all. And suddenly, the impact hypothesis for the magnetic field fell apart. This is how science works. You build a model, you test it, it fails. You build a better model, you test that one. It fails in a different way. You build an even better model, and slowly, over years and decades, the models get closer to reality. Not because any single model is right, but because each failure teaches you something about what reality actually looks like. Uranus has been one of the most prolific teachers in this regard. It has broken more models than almost any other planet, and every broken model has led to a better understanding of how planets work. That is the gift of a strange planet. Not answers, but better questions. Now let us think about the Kyper belt, the vast ring of icy bodies that lies beyond Neptune's orbit, stretching from about 30 astronomical units to perhaps 50 or more. This is the realm of Pluto and Eris and Makemake and thousands of smaller objects, the frozen remnants of the solar system's formation. Uranus has a complicated relationship with the Kyper belt. During the early solar system, when the giant planets were migrating and reshuffling their orbits in the event known as the Nice model, Uranus may have played a crucial role in scattering objects outward into the Kyper belt and inward toward the inner solar system. Some of the short-period comets that occasionally grace our skies may have been nudged onto their current orbits by gravitational interactions with Uranus billions of years ago. And some of Uranus's smaller, irregular moons, the ones that orbit at large distances and on tilted or retrograde orbits, may be captured Kuiper belt objects. These moons would have been drifting through the outer solar system when Uranus's gravity snagged them, pulling them into orbit and holding them there ever since. If this is true, then studying these small moons would tell us not just about Uranus, but about the composition and history of the Kuiper belt itself. The connections extend even further. When we study Uranus's rings, we are studying a system of particles that may have been created and replenished by the same processes that operate in the Kuiper belt. When we study Uranus's atmosphere, we are studying a chemical environment that shares ingredients with the icy bodies of the outer solar system. When we study Uranus's interior, we are studying the end product of the same accretion process that built comets and trans-Neptunian objects. Everything in the outer solar system is connected, and Uranus sits at the nexus of those connections, a bridge between the gas giants that dominate the middle solar system and the icy wilderness that lies beyond. Now let us return to the topic of seasons one more time, because there is an aspect we have not yet fully explored: the implications for Uranus's moons, because Uranus is, tipped on its side, its moons which orbit in the planet's equatorial plane, also trace out orbits that are nearly perpendicular to Uranus's orbit around the Sun. This means that the moons experience the same extreme seasons as the planet itself. During Uranus's solstice, the moons closest to the planet orbit in a pattern that takes them over the sunlit pole and then around to the dark pole, each orbit providing a full cycle of day and night. But the moons farther out, with longer orbital periods, can spend extended intervals in continuous sunlight or continuous darkness, depending on their position. This extreme seasonal illumination affects everything from the surface temperature of the moons to the potential for any atmospheric or geological activity. A moon that spends years in continuous sunlight will have a very different thermal profile from one that has been in darkness for decades. Any volatile compounds on the surface, water ice, ammonia ice, or carbon dioxide, could sublimate in the sunlight and refreeze in the dark, creating cycles of surface change that we have never observed. And here is an intriguing thought. If any of Uranus's moons do have subsurface oceans, the extreme seasonal changes in heating could drive periodic variations in ocean activity. More tidal heating during certain orbital configurations, combined with more solar heating during certain seasons, could create pulses of geological activity, episodes of cryovolcanism or plume eruption that come and go on timescales of decades. We would never see these with a single flyby. You need an orbiter. You need years of continuous observation. You need the kind of sustained attention that we have given to Jupiter's moons with Juno and to Saturn's moons with Cassini. And we have given Uranus none of it. Let us consider one more thing about the rings before we move on. The rings of Uranus are not just dark and thin. They are also surprisingly dynamic. Observations over the past several decades have shown that the rings are changing. The epsilon ring, the outermost and brightest of the main rings, varies in width as it orbits the planet, narrowing to as little as 20 kilometers in some places and widening to nearly 100 kilometers in others. This variation is maintained by two small moons, Cordelia and Ophelia, that orbit on either side of the ring and act as gravitational shepherds, confining the ring particles between them. But shepherd moons can only explain so much. The other rings do not all have identified shepherds, and some of them are so narrow that they should disperse in a matter of centuries without something to hold them in place. The question of what maintains these razor-thin rings has been open for decades. One possibility is that the rings are constantly being replenished by collisions between small moonlets that orbit within or near the ring system. These collisions would grind the moonlets down, producing fresh debris that replaces the material lost to spreading and orbital decay. In this model, the rings are not ancient leftovers, but ongoing creations, continuously recycled from a population of small bodies that orbit the planet in a perpetual state of slow destruction. This would make the rings of Uranus something like a cosmic recycling plant, breaking down old material and turning it into new ring particles in a cycle that has persisted for millions or billions of years. It would also mean that the rings we see today are not the same rings that existed 1 billion years ago, or even 100 million years ago. They are perpetually fresh, continuously renewed, even as they appear to be fading. And the recently discovered 28th moon, found by the James Webb Space Telescope in 2025, adds weight to this idea. This tiny moon, only about 10 kilometers across, orbits right at the edge of the inner ring system. It may be one of many small moonlets that interact with the rings, contributing material through collisions and helping to shape the ring structure through gravitational interactions. There could be dozens more moonlets like it, too small to detect even with Webb, hiding in the glare of the rings, quietly shaping the ring system through invisible interactions. A Uranus orbiter with the right instruments could find them, mapping the entire population of small moons and ring particles, and finally explaining how this faint dark ring system has survived for so long. The rings of Uranus are a puzzle within a puzzle, and like everything else about this planet, the answer is probably more interesting than anyone expects. Let us think about one more aspect of Uranus that deserves attention: its relationship with the Sun. At a distance of about 19 astronomical units, Uranus receives roughly 1/400th the amount of sunlight that Earth receives. At noon on Uranus, the Sun would appear as a small, bright point, far more luminous than any star, but unmistakably diminished from the blazing orb we know on Earth. You could look directly at it without squinting. Its warmth would be imperceptible, and yet, even this feeble sunlight has profound effects on the planet. It drives the photochemical reactions in the upper atmosphere that produce the methane haze. It provides the baseline energy that the planet must balance against its internal heat. And it governs the extreme seasonal cycle that shapes the planet's atmospheric dynamics over the course of its 84-year orbit. The relationship between Uranus and the Sun is a study in subtlety. On Earth, the Sun dominates everything. It drives our weather, our climate, our seasons, our biology. On Jupiter and Saturn, the Sun is still significant but beginning to share the stage with the planet's own internal heat. On Neptune, the internal heat actually exceeds the solar input, making the planet in some sense self-powered. On Uranus, the balance is delicate. The Sun provides most of the energy, but the internal heat, small as it is, plays a role that we are only beginning to understand. The interplay between the two energy sources determines the atmospheric temperature profile, the wind patterns, the cloud formation, and perhaps even the behavior of the magnetic field. And because the seasonal variations in solar input are so extreme, thanks to the axial tilt, this interplay changes dramatically over the course of each orbit. We are observing Uranus at one point in that cycle, just one, and we are trying to extrapolate from that single observation to a full understanding of a process that takes 84 years to complete. It is like trying to understand the Earth's ice ages by studying a single Tuesday in July. The humility required by this situation is, in its own way, beautiful. Science is at its best when it acknowledges what it does not know. And when it comes to Uranus, there is so much we do not know that the acknowledgement itself becomes a kind of map. A map of ignorance, yes, but also a map of possibility. Every blank space on that map is a place where discovery is waiting. Let us think about what those discoveries might be. Let us speculate, just for a moment, about what a Uranus orbiter might find when it finally arrives. Perhaps it will discover that the interior of Uranus is not 3 layers, but 5 or 10, with complex gradations of composition and phase that no current model predicts. Perhaps it will find that the diamond rain is even more widespread than we think, extending into regions where it influences the chemistry of the middle atmosphere in ways we have never considered. Perhaps it will discover active cryovolcanism on one of the moons, with plumes of water and ammonia erupting from a subsurface ocean, carrying organic molecules to the surface. Perhaps it will find that Miranda's chaotic terrain is even more varied in the northern hemisphere, which Voyager never photographed, with features that defy any current explanation. Perhaps it will discover new moons, dozens of them, tiny fragments of ancient collisions hiding in the ring system or lurking in distant inclined orbits. Perhaps it will find that the rings are far more structured than they appear from Earth, with fine details that reveal the gravitational fingerprints of unseen bodies. Perhaps it will discover that Uranus's magnetic field is even more complex than we thought, with multipolar components that shift and change on timescales of hours or days, driven by the chaotic motion of the supersonic water ocean. Perhaps it will find that the auroras are not just infrared, but also ultraviolet, invisible to Webb, but detectable by instruments aboard the orbiter. Or perhaps it will find something completely unexpected, something that no one has predicted, something that forces us to rethink not just our understanding of Uranus, but our understanding of planets in general. That is the thing about exploration. The most important discoveries are always the ones you did not see coming. And that is why we go. Not because we know what we will find, but because we know we will find something. And whatever it is, it will change us. Let us linger here a while longer, because there is one more dimension of the Uranus story that we have only touched on lightly, and it deserves a fuller exploration. It is the dimension of time. Not cosmic time, though that is important too. Human time. The time it takes to go from ignorance to understanding. The time it takes to build the instruments, secure the funding, design the spacecraft, and wait for it to cross the vast emptiness between here and there. The Voyager probes were conceived in the late 1960s, when the alignment of the outer planets offered a once-in-a-lifetime opportunity to visit all 4 gas and ice giants with a single spacecraft. The mission was approved in the early 1970s. The spacecraft were launched in 1977. Voyager 2 reached Uranus in 1986. The journey from concept to arrival took nearly 20 years. If a Uranus orbiter and probe is approved soon, and that is a significant if given current budget realities, it would follow a similar timeline. Design and construction in the late 2020s and early 2030s. Launch in the mid-2030s. Arrival in the late 2040s. That is another 2 decades at minimum from decision to discovery. 2 decades, an entire generation. Children who are not yet born will be adults by the time a spacecraft enters orbit around Uranus. Scientists who are graduate students today will be department chairs or retired. The world will be different in ways we cannot predict. And yet, the investment is worth it, because the questions that Uranus poses are not going to become less important over time. If anything, they will become more urgent, as we discover more exoplanets, more sub-Neptunes, more worlds that look like they might share something in common with our local ice giants. The need to understand Uranus and Neptune will only grow. We cannot study exoplanets up close. They are too far away. We can observe them as dots of light transiting distant stars, measure their masses and radii, and sometimes detect the chemical signatures of their atmospheres. But we cannot send spacecraft to them. Not with current technology. Not for centuries, if ever. What we can do is study our own ice giants in exquisite detail and use what we learn to interpret the data from those distant worlds. Uranus and Neptune are our laboratory. They are the only examples of ice giant planets that we can reach, orbit, probe, and study at close range. Everything we learn about them becomes a lens through which we can view the billions of similar worlds scattered across the galaxy. This is not an abstract benefit. This is practical, essential science. Without understanding ice giants, we cannot accurately model the atmospheres of sub-Neptune exoplanets. We cannot predict their weather, their chemistry, their magnetic fields, or their potential for harboring life. We cannot even accurately classify them. We are, in a very real sense, trying to read a book written in a language we do not speak, And Uranus is the dictionary we have been neglecting. The irony is not lost on anyone. The most ignored planet in our solar system holds the keys to understanding the most common type of planet in the universe. If that is not a cosmic joke, it is at least a cosmic lesson in humility. The universe does not arrange itself for our convenience. The answers are not always where we expect them to be. Sometimes they are hiding in the most overlooked, most neglected, most underestimated places. Like a pale blue-green planet, rolling on its side, at the edge of everything we know. Let us think about one more thing. The sound of Uranus, or rather, the silence. There is no sound on Uranus, of course. Not in the way we experience sound on Earth. Sound requires a medium, molecules vibrating and transmitting pressure waves to our ears. Uranus has an atmosphere, so in principle, sound waves could propagate through it. But there is no one there to hear them. No ear has ever registered the howl of Uranian winds, the crack of Uranian lightning, the deep subsonic rumble of atmospheric convection, moving masses of gas at hundreds of kilometers per hour. If you could somehow protect yourself from the cold and the pressure and the toxicity, and stand in the upper atmosphere of Uranus, what would you hear? The wind, certainly. A constant roaring, keening wind, blowing at speeds that would turn any earthly hurricane into a gentle breeze. The wind would be the dominant sound, the soundtrack of a planet where weather operates on a scale that dwarfs anything in our experience. Below the wind, you might hear the crackle and boom of lightning. Not the sharp, percussive crack of earthly lightning, but a deeper, more sustained rumble. The sound of electrical discharges playing through clouds of hydrogen, sulfide and ammonia at pressures that amplify and distort the sound in ways we can only guess at. And below that, far below, in the deep interior where sound waves propagate through a medium denser and hotter than anything on Earth, there might be other sounds. The groan and shift of exotic materials under unimaginable pressure, the crystalline chime of diamonds forming and falling, the slow, deep pulse of convective currents moving through superionic ice. We will never hear these sounds, not directly, but we can imagine them, and in imagining them, we connect, in some small way, with a world that is profoundly alien and yet made of the same atoms and governed by the same physical laws as the one we call home. That connection is one of the most beautiful things about science. It allows us to reach across the void and touch, however lightly, a reality that is utterly beyond our direct experience. And with that thought, let us begin our descent towards sleep, but slowly, gently, the way Uranus does everything, in its own time. Let us think, one last time, about what we have learned tonight. Not just the facts, though the facts are extraordinary. A planet tipped on its side. A magnetic field that wobbles and tilts. An interior where diamonds rain through exotic ice. Moons named for Shakespeare's characters, carrying the scars of ancient violence. Rings darker than charcoal, nearly invisible against the void. A heat source that took 40 years to find. A magnetosphere caught in a storm, the one time anyone looked at it. The tallest cliff in the solar system, on a moon smaller than some countries. And the quiet, persistent, astonishing fact that planets like Uranus may be the most common type of world in the galaxy. These facts are worth knowing. They are worth marveling at. They are worth carrying with you as you drift towards sleep, letting them settle into your mind the way sediment settles on a riverbed, each grain finding its place among the others. But beyond the facts, there is something else. Something harder to name. A feeling, perhaps. The feeling you get when you realize that the universe is not only stranger than you imagined, but stranger than you can imagine. That for every question we have answered, a dozen more are waiting. That for every planet we have explored, 1,000 more are drifting in the dark, carrying secrets we cannot even guess at. Uranus teaches us this better than any other world, because Uranus is the planet we thought we knew, the planet we dismissed as boring, the planet we visited once, glanced at, and moved on. And then, decades later, we looked again and realized we had been wrong about almost everything. The heat was there. We just could not see it. The atmosphere was active. We just visited at the wrong time. The magnetic field was behaving normally for an ice giant. We just did not know what normal looked like. The moons were geologically rich. We just did not have the instruments to see it. The rings were maintained by processes we had not imagined. The whole planet was more dynamic, more complex, more alive than anyone had suspected. And all of this from a world we thought was dead. If Uranus can surprise us this thoroughly, what else is hiding in the places we have not looked? What other worlds, what other moons, what other corners of the cosmos are waiting to reveal their secrets the moment we decide to pay attention? The universe rewards those who look closely. It always has. From the moment Herschel pointed his homemade telescope at what he thought was a comet and discovered a planet, to the moment Webb turned its infrared eyes toward that same planet and revealed auroras and atmospheric structures invisible to every previous instrument, the story of Uranus has been a story of looking more carefully and being rewarded with wonder. That story is not over. It is barely beginning. The best chapters have not been written yet. They are out there waiting in the cold and the quiet on a planet that rolls through the dark at the edge of everything. We just have to go and read them. So close your eyes. Let the darkness come. Let the silence settle around you like the silence that surrounds Uranus, deep and vast and full of things you cannot see but know are there. Think about the ice giant. Think about its patience. Think about the 4.5 billion years it has been spinning on its side, carrying its scars, keeping its secrets, rolling through the cold with a quiet dignity that asks nothing of anyone. Think about the diamonds, falling through the dark interior, each one a tiny crystal of carbon compressed into perfection by forces beyond comprehension, falling like snow, falling like tears, falling like the answers to questions we have not yet learned to ask. Think about the moons orbiting in their patient circles, their surfaces etched with the evidence of a history we have only begun to read. Miranda with its impossible cliff, Ariel with its bright, scarred face, Titania and Oberon, named for fairy royalty, keeping their own counsel in the outer, dark. Think about the rings, thin and dark and barely there, whispering against the void like the memory of something that was once much grander. And think about this. Right now, at this very moment, light from the sun is reaching Uranus. It has been traveling for 2 hours and 40 minutes. By the time it arrives, it is faint. So faint that a human standing on the cloud tops would barely feel its warmth. But it is there. Light from our star, touching a world that few people think about and fewer still have ever tried to understand. That light does not judge. It does not choose favorites. It illuminates Uranus with the same impartial glow that it gives to Earth, to Jupiter, to every mote of dust that drifts between the stars. And in that light, Uranus is revealed for what it truly is. Not the forgotten planet, not the broken planet, not the punchline of a joke, but a world, a real, physical, extraordinary world, full of mystery, full of beauty, full of questions that deserve answers. Let us now turn to one final thought. A thought about the future. Not the future of Uranus, which will continue to roll through the dark for billions of years regardless of what we do, but the future of our understanding, the future of discovery. Right now, at this very moment, there are scientists working on proposals for a Uranus mission, engineers designing instruments that could withstand the cold and the radiation and the long journey to the outer solar system, graduate students writing dissertations about the magnetic field, the atmospheric chemistry, the thermal evolution of ice giants. Teams planning observation campaigns with Webb, coordinating with ground-based observatories, preparing for the next stellar occultation that will let them measure the planet's atmosphere from nearly 2 billion miles away. The work is happening. Slowly, patiently, methodically, the way science always works, not with sudden breakthroughs or dramatic revelations, but with a steady accumulation of data. Each measurement a little more precise than the last, each model a little more sophisticated, each observation revealing a little more of the truth. And someday, perhaps 20 or 30 years from now, a spacecraft will fire its engines and begin the long journey to Uranus. It will take more than a decade to get there. And when it arrives, it will begin a systematic survey of the planet, its atmosphere, its interior, its magnetic field, its rings, its moons. It will send back images that make the Voyager photographs look like cave paintings. It will measure things that no one has ever measured. It will answer questions that have been open since 1986 and ask new questions that we cannot even imagine today. And on that day, Uranus will finally step out of the shadows, the forgotten planet, the broken planet, the planet that nobody cared about. It will reveal itself not as an oddity or a misfit, but as a key to understanding the most common type of planet in the galaxy, a key to unlocking the history of our own solar system, a key to everything we do not yet know about how worlds are made and how they work and what they become over the vast, slow reaches of cosmic time. Until then, the planet waits, rolling on its side, spinning in the dark, its diamond rain falling silently through the depths, its magnetic field twisting in the void, its moons carrying the scars of ancient violence, its rings fading slowly like the last light of a candle in a room that has been empty for a very, very long time. Uranus does not need us, but we need Uranus, because in its silence there are answers, in its darkness there is light, and in its patience there is a lesson that we would all do well to learn. Some things take time to understand, some questions do not have easy answers, and some planets, the ones that break every rule and defy every expectation, are the ones most worth studying. Sleep well tonight. And as you drift off, think about the ice giant rolling through the dark at the edge of everything. Think about the diamonds falling through the silence. Think about the auroras glowing in wavelengths we cannot see. Think about the moons, named for Shakespeare's characters, orbiting a world that is stranger than any story ever written. And think about this. Somewhere out there, in the cold and the quiet and the dark, a planet is keeping secrets. Secrets that are 4.5 billion years old. Secrets that might explain how the universe builds its worlds. And all we have to do is go and look. Close your eyes now. Let the silence wrap around you like the silence that wraps around Uranus. Let the darkness come, soft and deep and full of hidden things. And know that out there, in the cold reaches of our solar system, a world is waiting, patient, quiet, turning on its side in the endless dark, its diamonds falling, its secrets intact, its story still being written, one discovery at a time. Good night. If you made it here, you already know what this feels like. That quiet, that drift. But every night it ends. The video stops. The silence wakes you. And you're reaching for your phone at 3 a.m., choosing something new when all you wanted was to stay asleep. Beyond the Stars was made for that moment. 5 deep sleep experiences, hours long. No ads, no endings. Just the night, all the way through. Yours tonight for a one-time purchase. Begin now at mycosmicdrift.com.